So thank you all for joining this Kokkos Tea Time, February 2026 Kokkos Tea Time. And today we're extremely happy to welcome Jolly Chen. Jolly, you're working at CERN and are affiliated with the University of Twente. And you will tell us about using reflection in C++ to abstract data layout. So, Jolly, the floor is yours.
Yes, thank you for the introduction. So yes, I will be talking about C++ reflection for data layout abstraction. So the problem is that good performance requires good memory access patterns, which depend on, for example, the data layout. And to illustrate this, I have on the right an image where I have the results of a benchmark that I did using the same kernel, the same architecture, but with different layouts for the objects that I used in the kernel. So on the x-axis, I have the different runtimes that I measured. And on the y-axis, I have the frequency or the number of layouts that resulted in a specific runtime. And we see that there's quite a big spread in this image, which shows that the layout or the memory access pattern can have a pretty significant impact on the performance. And of course, this picture could look different if we had a different architecture or a different computation, which makes it difficult to choose what the optimal layout is. So a common dilemma that people face is choosing between array of structures and a structure of arrays, so AOS or SOA for short. And in C++, the way you can change your layout is by redefining your data structures. So on the left, we have what you could write to get a AOS layout. So in this case, the data members for a structure are contiguous in memory, while on the right-hand side, we have what you would write for in SOA, where the elements for each data member are contiguous in memory. So we can see that changing between AOS and SOA is not necessarily difficult. It just requires a lot of effort to rewrite your code. But another thing is that if you switch your data layouts, it can also affect the way you need to access your data. So for example, on the left-hand side on line 11, if you read this, you could maybe read this as the ID of the third particle, which is fairly intuitive. But then with the SOA, you would read this as the third ID of particles, which doesn't necessarily mean something. So what we want here is to decouple the memory organization from the logical data access so that we can easily switch between the AOS and the SOA. And then we also want to keep an intuitive access style, which in this case is the AOS style of accessing. So now that I gave a brief introduction on why we want a data layer abstraction and what the exact goal is, in the rest of the talk, I will be talking about C++ reflection. So I will give a brief introduction. And then I will give 3 different examples on how you could use reflection to create this abstraction. At the end, I will also give a performance comparison of these abstractions compared to manually defining your SOAs in terms of runtime and compile time. And then I will also give a few comments on my experience with reflection. So C++26 reflection gives us 2 new operators. The first one allows you to kind of lift an operand to a reflection value. And regardless of the type of X, you will get a reflection value of type std_method_info. And once you have a reflection value, you can also return back to a unreflected value, or I guess you could call that normal code, using a splice operator. We can also query the data members of a reflected value. So for example, with non-static data members off, we can ask what the data members are of a struct S, and we can specify the access context of this call, which allows you to, for example, exclude private data members. And this invocation to non-static data members off returns a std vector of std_method_info. So this is a method that we use a lot. And since this is a really long line, I will be shortening this to NSDMS in the rest of my slides. We can also define structures using define aggregate. So this takes as parameters the reflection of the structs that you want to define and a list of data member specifications. And each specification takes in the data type that you would want to have for this data member and optionally a name and an alignment. So in this example, we are defining struct S as a structure that has an integer named I and a double named K. The proposal for C++36 reflection, so called P2996, actually already gives us an example of how you can turn a struct to a struct-of-arrays. So for example, if you have a structure T that has an integer and a float, you can plug this into this call to struct-of-arrays impl, and then you get back a new structure impl that has the array version of each data member. So it does this by getting the data members of the original structure T, and then for each data member in T, we are constructing an array type of the data member type. So we are getting the type of the data member using type of, and then we are substituting this into the template std array. And all the parameters need to be reflection parameters. So they need to be of type std meta info. So we are calling reflect constant to take this n, which is a size t, as a reflection of the n. And so this gives us the reflection of the type std array int or the type std array float. So once we have the array type, we can put this into a data member specification and then give it the same name as in the original structure by asking the name of the reflection using identifier of. And we put all of this into a list of new members, which we then put into define aggregate that defines this impulse structure that was defined here. One last thing that I want to point out in this example is that all the reflection methods are const eval, which means that you need to put them into a const eval block like this.
Jolly, you have a question in the chat.
Okay, yes.
Cameron asked, I assume the number of structs in the AOS needs to be known at compile time, right?
Yes, I can't really imagine a struct where you would not know this at compile time. So I'm not sure exactly if I understand the question fully.
Yeah, just to clarify, so you have the 3 in the right-hand side.
This, yes.
Yeah.
Yes, I believe this needs to be known in compile time for you to be able to reflect it, because it needs to be a constant. You reflect a constant. Got it. Okay, thank you. Yes. Thank you for your question. So hopefully this is clear, because this concept will be used in all the following slides. So we have a way to automate converting AOS members to SOA now, but how do we keep the AOS style access semantics? So one way we can do that is by defining the operator, the index operator, but can we do this with define aggregate? Well, define aggregate has a few limitations because it can only define data members. So you can't define, for example, functions in the structure. And it can only do that for incomplete types. So for example, in the first line, we have an incomplete structure that is declared but not defined. This we can define aggregate. But then if we have a structure that has an index operator inside of it defined, then we can't call define aggregate on this because this will give us a redefinition error. if we have a templated structure, then we can define aggregate a specialization of the template, because that would be a new structure. But since it is a new structure, we won't have access to the members that are in the base template. So this would allow us to generate more structures than one using one declaration, but it still doesn't solve the problem of having an index operator. So what we can do is create a wrapper that inherits from a base class that contains the SOA-ified members. So we would call define aggregate on this base structure, but then outside of this base structure and inside the wrapper, we define an index operator. And the index operator then returns a version of the original structure that contains reference data types, so that we can reference back into the SOA members while still keeping the AOS style view of the original structure. So before I go into the implementation details of the wrapper, I am going to show you the user interface so that you can get a better idea of what we are working towards. So the original structure is, for example, a point with 3 data members. And then we want to create an SOA version of this, which we can do by putting it into the wrapper. And then as a second argument, we give stat vector to indicate that we want to have in the SOA each member as a stat vector member. And then on the last line, we have the access to the data as an AOS. And we can do this by, as shown previously, returning a view that has, so in this case, the view would be the point structure that has these reference types that point into the SOA members in the wrapper. So in this original structure, we already have the reference types. We could allow the user to simply specify value types, and then we generate, using reflection, these reference types. So we generate this proxy view, but then we again would lose the access to the member methods that the user defines. So that's a bit unfortunate. So the wrapper is implemented using a structure that we call wrapper generator. And this wrapper generator takes as a template parameter, as shown previously, the original structure and the container type that we want to have for each SOA member. And this wrapper generator has a declaration for a base structure that we define. We define this using a helper method called transform methods, which takes the data members of the original structure and then creates a new data member specification for each new data member. So it does this by applying a function, which in this case, in define aggregate, is the substitute onto each data member. And we again give it the same name. So in this define aggregate, we are substituting the type of each data member into this container type that we provided. And we need to remove the reference type so that we don't have stat vector float reference, but just stat vector float, for example. So this would result into this for the example in the beginning. So now that we have the data members, we need to define an index operator. So in this wrapper generator, we are defining a wrapper class that inherits from the base class so that we have the access to the data members. And then the index operator returns the original structure. So it essentially returns the point structure populated with elements from the original SOA members. And it does this by using this helper lambda that indexes onto each data member inside the base class. So this non-static data members off returns a stat vector info, which is not considered a pack. So we need a helper lambda that takes an index sequence so that we have a pack that we can unpack, so that we can apply this index operator to each data member. So this is a construct that we use quite often, applying something to each data member. But hopefully in the future, we will have something like a range splice that allows us to essentially get a stit vector of info as a pack, which we can then splice so that we get the unreflected version of a pack, and then we can just unpack this. So these were the main implementation details for the SOA wrapper. The second thing I want to show you is SOA wrapper with token injection. So token sequences are a feature that are not going to be part of C++26, but it's part of a separate proposal on reflection that could be very interesting. So this proposal adds another new operator that allows you to define a token sequence. So essentially a piece of code that you can then inject somewhere. And you can also access context outside of the token sequence using 3 interpolators. So for example, if you want to call a reflection method like type off or identifier off inside your token sequence, you need to put this into / round brackets so that it takes not actually type off, but the return value of type off. You can also create new identifiers using \id by concatenating different string-like values. And you can also put an existing token sequence into another sequence by using \tokens. So using token injection, we can have a user interface. We can have an SOA wrapper with an original structure that has more complex types. So previously we had only scalar types, but now we also have a nested structure. And we also have a structure that would be a vector. So again, like in the previous example, we only want to have reference types. So we use span to refer to a stit vector. And then at the bottom, you can see that we can also access nested structures like an AOS. So the wrapper definition in this case would be as follows. We have a storage where we will put all the data elements for the SOA members. And we have this, so this is a function that I've defined myself, gen SOA members, that will generate the token sequences for each declaration. So the desired result of this is as follows. So this is the example that we had before. And for each data member, we want to have a containerized version of it. And for the nested structure, we are recursively SOAifying the structures so that we can get this AOS style syntax even with the nested structures. For the vector type, so there are different ways in which you can SOAify a vector. In this case, we are essentially putting the elements for each, so the vectors for each element in OSOA in the same container. So we need to keep some metadata to keep track of where the vector for each element starts. And to do this, we use the following function. So it's a lot of code, but hopefully if I go slow, it's understandable. So we start with a list of tokens. So this list will keep a list of sequences, token sequences that contain a declaration. And then we also keep track of which nested structures we have already SOAified so that we don't redeclare them when we have multiple declarations for the same nested type. So we are, again, iterating over the data members, and then we have different cases for each data type. So what I want to highlight here is that in this case, if we have a container type, we want to essentially inject this. We want to inject stdspan float vector and stds vector size t vector of offsets. And to do this, you create a token sequence like this. And instead of having to use substitute to create this stdspan float, we can just directly type stdspan. And we, in this case, we splice the data type of the original structure, and then we specify the identifier of the original data member. And here you can see that we can concatenate the name of the original structure with a new string, such as _offsets. And we can recursively call this function to build a list of declarations. And we can concatenate the token sequences by using the interpolator \tokens, so that the list of token sequences becomes one token sequence. So on this slide, I'm showing the random access operator. And this shows another way in which you can concatenate token sequences using a list builder. So this creates a comma-separated token sequence. So what this is doing is, again, it's looping over the data members inside of the original structure. And then we are gathering the code that you would need to access the original, to access the elements within the SOA members, to populate this view structure that we have provided to the wrapper. So this this access operator would, for this example, return the code as shown here. So for completeness, I have the code for the access operator here, but it uses essentially the same concepts as I've shown before. So, and since I also don't have a lot of time left, I will not go into detail here. Instead, I want you to show the third approach, which is different from the other two, for defining an SOA. So in this case, I have the original structure S with 3 data members, and I can decompose this into 2 separate substructures that has a subset of the original data members. So in this case, I do that by applying a split operation that takes the arguments the list of data members that I want to have in each substructure. So in this case, we have in the first substructure only the 0th data member, and in the second substructure we have data members 2 and 1. So in this, so we can also reorder the data members like this. And then after decomposing, we can also recompose it again into a container, so that we have a container that contains only the first substructure, so that this blue data member is contiguous in memory. And then we can have a container for the other substructure, so that we have members 2 and 1 contiguous in memory. And again, we can define an index operator that refers back to these SOA members, or these containerized members, to get the original access syntax as in struct-s. So the interface for this would be as follows. So we have, again, a point structure with some basic data members. We have a declaration for a substructure that we will define using define aggregate. And that happens in this decompose step using split struct. And this takes, so the original structure, the declaration for the substructure that we want to define, and a list of split operations. And then we can compose this again by putting this into a partition container class that I will show later. So one thing to highlight here is that this split struct is actually taking a list of vectors at compile time. And we can do this thanks to a new function called define static array, which promotes compile time values to static storage. So we can create structures using the split struct, and this is done using this function here. So this the split operations are essentially a vector of compile time values, and here we again need to unpack the list of values in the arrays here. So we are creating a array of reflected constants so that we can put this as template parameters of the subpoint. So this would essentially result into this. And then for the partition container, we can define aggregate again, the declaration that contains the factorized version or the stitsman version of the different substructures. And an important thing here is that we need to create a mapping to remember how the data members in the partitioned structure map back into the original structure. So I'm not going to go into detail in this code sample, but what this essentially does is it creates a mapping that contains a pair of indices that, for example, here the 0th data member indicates that it's in the second substructure, and then on the 0th index of the so that it's the first data member of the second substructure. And then we also have a random access operator that uses this mapping to populate the proxy reference again. So now I'm going to go into the performance comparison. So there are 3 different compilers available which allow you to compile reflection code. There is the fork of Clang, which I believe is the most up-to-date. We also have a experimental reflection frontend from EDG, which supports token sequences, but is not very up-to-date with the P2996 features. And then there's recently also a version from GCC that has been merged into Trunk, but I have not been able to test this yet. So in the performance results, the results that I will show in the next slide, they essentially are 3 different computations. And the goal is to show that these abstractions have no overhead at runtime because everything happens at compile time. And indeed, I can probably go very quickly through these slides because these plots show on the x-axis different input sizes and on the y-axis the runtime. And I have for the different versions a different color, but you can only see one color because they are all overlapping, which shows that indeed there's no runtime change due to the abstraction. And the same for the version with token injection. What's a bit more interesting is that the compile time changes a bit. So for the versions that I've compiled with the Clang reflection compiler, which is the manual version, the wrapper version, and the struct splitter version, I see that there's a bit of an increase in compile time when I'm using reflection. But have to say that the compiler for implementations are still experimental. So this can change. And I saw that there's not really an increase with the EDG version, but it's a different compiler, so it's not something you can directly compare with the Clang version. Some last comments on my experience with reflection are that, so personally, I really found metaprogramming with reflection a lot more straightforward than with, for example, templates, because it allows you to kind of iterate over types, and you can directly query what different information on a type instead of doing some tricks with parameter unpacking and trying to get the last element of a pack and things like that. I also really liked trying out token sequences. It felt really incredible, but it felt really powerful. But I suppose this also comes at a cost because you can do a lot of weird things, which are sometimes hard to debug. Two things that I've already mentioned before is that the fine aggregate has quite a limited scope. I have had several occasions where I wanted to do something more than just defining new members, but I had to find a workaround to do that. And would also be nice to have something like a range apply so that I can apply something on the range of data members. The last thing is that the error messages are sometimes not very clear. So, for example, if I call a reflection method on something that isn't quite the right reflection value, then I get error messages that are not very descriptive yet. I suppose this will also change, or hopefully this will also change, but overall, in the end, I did find a way to implement what I wanted. So hopefully this kind of inspired you as well to try reflection. So I have the different links for the different implementations. I also have some links for the code that I've shown. So that's it for me. And any questions?
Thank you very much, Jolly. Mark, do you want to unmute yourself and ask your question?
Oh yeah, hi Damian. Can you hear me okay?
Yeah. Oh, yes.
Oh, hi Jolly. Great talk, thank you. I just wanted to ask if you had any feedback for the design of token reflection. I know they're still working on the feature. There may be changes to it. Andre is my colleague. If you have feedback that you'd like to pass along to him, either now or via email later, please feel welcome to do so.
Yes. It's been a while since I worked with the token sequences, so I can't think of feedback right now. But if I think of anything later, I'll definitely send it. Yes.
Thank you.
There's another question from Cameron who asked whether the CPP insights can help debugging this or whether reflection is too new.
I have not tried, so I don't think I can comment on this.
I would bet it's too new, but Jolly, anyone else has a question? Okay, while they're thinking, I'm going to ask you one. The result you show, is it from a small research code, or is it you went into a real application and you did these changes there?
No, these are small examples, so it's not it's not real life code in that sense. Yes.
Did you interact much with application developers to show them a bit what reflection can do? Did you already see reaction? Do you have thoughts on how hard it's going to be for a real application to accept this? Because it's clearly very powerful, but it's a lot to take for people who are not familiar with reflection.
I can say that I have been showing it to people here at CERN. They they seem to be very excited to apply it to their current code. So I'm currently working on SOA abstractions with reflection, but we also have some other people working on SOA abstractions without reflection. But from what I've sensed is that the idea is that once they have that and reflection is there, they want to move on to reflection. So people seem to be enthusiastic here.
I see another question on the chat. Do you have a way? Do you have a way of seeing the generated code, the C++ code after generation?
Unfortunately, no. That would be really nice. Although with the token sequences, you have a method called report tokens. So this allows you to print the token sequences that you're creating while you're compiling. So it ends up in your compilation message. So in that case, you do kind of have an idea of what you're creating, but with the P2996 reflection, you don't really have a way to see what's being generated.
Mm-hmm. Do you have any good reference of that have best practices or patterns that can be used for this?
I would like to have something like that myself. I think looking at the examples in the proposal could help, because that kind of gives you an idea of what the designers intended you to do. But yes, it would be very nice to have guidelines for things you should not do.
And I was curious, what's your workflow as you were working with reflection? Are you building the latest version of this compiler yourself on a regular basis? Do you do a lot on Godbolt and rely on their deployment? How have you been working?
I think it's a mix of both. So I have the latest version compiled locally, but then when I want to try something small, I do often turn to Godbolt. So it's a bit of both. And when I'm writing reflection code, what helped me a lot is kind of writing the manual version first to kind of see, okay, this is what I want to end up with. And then I try to translate that into reflection.
Out of curiosity, what's your background? Were you a computer engineer who learned what the application were doing, or were you coming from the world of application and you were looking for a better way of doing all of these things?
So my background is I did a bachelor and a master in computer science, so a lot of programming, I suppose. I'm also doing a PhD in computer science right now, so but I would say I have probably way less experience with C++ than the audience here, since I started programming C++ full-time since only 2 or 3 years ago.
It's hard to believe when we see what you can do now.
Yeah.
Do we have any other question? Feel free to unmute yourself if you have a question. Okay, then let's thank the speaker. Thank you very much, Jolly. It was really good talk. I enjoyed it a lot. All right, thank you so much.
Thank you.